So there's this quote from Einstein that says that if you can't explain something to a 6-year-old, then you don't really understand it yourself. And I just think that's really silly because 6-year-olds are very young. They don't have a lot of life experience. They don't know differential equations. What do you mean if you can't explain it to them, then you don't understand it? Isn't it on them? I mean, of course, you could take any idea and just smooth it and cartoonize it so much that it's not even close to the actual idea and shove it down a 6-year-old's throat, and they might be like, okay, I get it. But do they get it? Have you seen those videos where they're like, machine learning at 5 different age groups, and they take like a child and they give them like, here's kind of what machine learning is. Then they take like a 10-year-old and then like an adult, you know? You don't think the 5-year-old in that video actually learned machine learning, do you? Like, that 5-year-old explanation was for you, the adult viewer, to get like a grounding so you can learn like the higher level idea. If you grab that 5-year-old, don't go around grabbing 5-year-olds, but if you grabbed them 26 days later and you were like, explain machine learning, child, they wouldn't know. They don't know. And actually, my favorite Einstein quote is the one about how like 90% of the quotes that are quoted to Einstein aren't actually Einstein quotes. Einstein didn't say this. Doesn't that suck for Einstein? Has anyone ever talked about how like people just make up stuff and they say Einstein said it? That sucks for him. I mean, he's dead, he doesn't care, but that sucks for him. But he didn't say this. And also, it just doesn't really make sense. And I would like to give you an example today of something you can't explain in a 30-minute YouTube video by doing a 30-minute YouTube video on why you can't explain the thing. This video is about QCD, quantum chromodynamics. So I thought this would be fun just because people are interested in what QCD is, but it's so complicated that you can't explain actually what QCD is. So I came up with like a nice little recipe for QCD so you can understand enough about it to understand why you don't understand it. Does that make sense? That's what I'm trying to do. I'm going to explain why I can't explain it. So let's start with some definitions. QCD is a field theory for what goes on inside protons and neutrons. So if you have like a helium atom, you know you have 2 electrons zooming around the outside of it, and deep inside that is the nucleus, where you have 2 protons and 2 neutrons. For some helium, some helium's different. And that's kind of interesting, right? Because protons are positively charged boys, and yet they're stuck together. Where your experience with magnets is that if you tried to take 2 positively charged boys and shove them together, you can't do that because the electromagnetic force would like push them apart. So QCD describes the strong force, which is the force that allows those positively charged boys to be held so tightly together, even though they're the same charge, and the electromagnetic force would try to rip them apart. A lot of people will compare the strong force to the electric force because the electric force, you have electric charge, you know, the sides of a bar magnet, positive and negative. An electron is a negatively charged subatomic particle, and a proton is a positively charged one. With the strong force, you have something called color charges, where there are 3. So you have red, blue, and green charges, and those add up to make a neutral color charge. Just like a positive and negative charge would add up to make a neutral electric charge. So QCD has color charge, which is why it's called QCD, quantum chromo for color dynamics. It's kind of funny how often people are like, I'm going to talk about QCD, and then they just end up talking about QED, quantum electrodynamics. They describe the electric force instead of the strong force. And it really goes back to the point of this video, which is that this is a very complicated topic. Even if you were in physics graduate school and you signed up for like a summer lecture series called Introduction to QCD, the first 8 of those 10 lectures would be about QED. It's kind of a joke at this point. In QED, in quantum electrodynamics, you're just studying the force of electromagnetism. You have the photon, which mediates the force between electrons, okay? The photon is a massless, chargeless particle. When you compare that to QCD, there is a particle that mediates the force of the strong force, but this particle is called a gluon. And unlike in the electromagnetic force, where there's just one photon, a gluon has 8 types. There are a bunch of different types of gluons. You can see how already QCD is just so much more complicated than QED. The gluons interact with quarks, which are the fundamental subatomic particles deep inside a proton. So every proton has 3 quarks, every neutron has 3 quarks, and when those guys interact with each other, they exchange gluons. Compare it to QED, where when electrons interact with each other, they exchange photons. So the different types of quarks are called flavors. I hate it. Like top, bottom, strange, charm, up, down. And then they also have colors, red, blue, and green, which denote their color charge. Yeah. The biggest difference between QED and QCD is the gluons of QCD have color charge, where photons are chargeless. So photons themselves do not interact with each other. They don't care about other photons, right? The way a photon is emitted from an electron because of the an electromagnetic interaction, it doesn't really matter if that happens amongst a bunch of other photons. The photons are fine to chill on their own. Gluons have charge. So if there is a gluon around another gluon, they are going to interact with each other as well as with the quarks inside that proton. And this makes things incredibly complicated because you got a lot of stuff going on. The fact that gluons interact is the reason that the force is called the strong force. If a quark tries to escape a proton, the gluons feel that force and start interacting with that quark, but also with themselves, and they start pulling that quark back into the proton. The further the quark gets away, the stronger that strong force is. And this will happen amongst protons in the nucleus. The reason the nucleus can hold a bunch of positive charge tightly bound is because of the strong force. It's because the gluons are interacting with themselves in addition to the quarks that make up those protons. They're called gluons because they stick things together like glue. I think one of the reasons I think QCD is hard to talk about is because I find all those definitions very boring. Like, to set the stage for QCD, you need to throw the standard model chart up and be like, look at all these boys, look at all these quarks, look how their masses increase to the right, look at how their charges differ. Do you know that you only find most of these in particle accelerators? Like, all of the interesting stuff happens in quantum electrodynamics. It's so much more fun to talk about. QCD is just protons, and like, maybe I'm just not into it. Maybe this isn't like you can't explain QCD in 30 minutes. Maybe this is like I can't, because I find it like just a little boring. It's just a little bit boring. Like, who cares about protons? All the good stuff is the electrons. It doesn't matter. Those were the definitions. We're done with that. I think this is the interesting part. So what I've done is I've set up a little recipe so you can follow the thinking on how you get to quantum chromodynamics. It's not a historical chronological account. This is just how you would go about writing down QCD if you were going to do that. And I am not going to write down, like, I'm not going to derive the Dirac equation for you. That would take hours. We can't do it. I have specifically arranged this in a way I find intuitive and interesting, and I hope it is for you, but I'm not a professional science communicator, so like, what do I know? Anyway, this is the recipe for QCD. To start, you need a little bit of quantum mechanics. In general, classical mechanics was a very successful way to describe macro objects, but once we started looking at little teeny tiny things, it started failing because the quantum mechanical world is different from the classical world. And to accurately describe the classical world, you kind of need to know what's going on. So in quantum mechanics, you have a wave function to describe a quantum mechanical particle like an electron. Particles that are quantum mechanical have wave-particle duality. Sometimes they behave like waves, sometimes they behave like particles, and it's the description of them as a wave that allows you to make predictions on their behavior. The wave function for an electron gives us like a probability amplitude, and from that you can get a probability density function. And that probability density function will allow you to predict where an electron will be after you've done an experiment on it and measured it. And there are two very important things happening there. The first is that it is a probability. You cannot tell where a quantum mechanical particle will be. You only know a probability distribution of where it could be and how likely each of those spaces are. So it's really important to remember that the results from field theories are probability distributions. You don't know what's going to happen. It's not like macroscopic objects where you throw up a ball and you can predict where it's going to fall. You throw photons at a wall, you know a certain percentage of them will be absorbed, a certain percentage of them will be reflected, and you can calculate the probability of that event happening for each photon. And the way you check that mathematical description is by doing a ton of measurements. This field of field theory is just steeped in experimental verification. How do you test that 86% of the time the electron is going to do this? You run 100 experiments and you make sure it does that 86% of the time. The next thing you're going to do is add a little bit of relativity to your quantum mechanics. So quantum mechanics was this way to describe things that are really small. You have this probabilistic behavior in particles that sometimes act like waves. Oh, it's so interesting. Relativity, on the other hand, is like Einstein's little baby, right? He uses it to describe the behavior of things that are going super fast or have really high energy. And if you want to do QCD, you need to add relativity and account for both of those things in your theory. This is sometimes called RQM, or relativistic quantum mechanics, and the most famous thing from this is the Dirac equation. So the Dirac equation combines things from quantum mechanics, the energy and momentum operators on the wave function, and to it he adds Einstein's relativistic energy relation. So you have quantum mechanics and also relativity all in one equation. The Dirac equation describes the behavior of spin 1/2 particles, so electrons and also quarks, but Dirac didn't know about quarks at the time. The most famous, interesting result from the Dirac equation I have mentioned before on this channel. The Dirac function, unlike the Schrödinger equation, which talks about electrons and kind of stays in this like positive domain, the Dirac equation allows you to move below zero to the negative domain as well. So in the Dirac equation, you have electrons that are spin up, electrons that are spin down, and anti-electrons that are spin up, and anti-electrons that are spin down. Just adding relativity to basic quantum mechanics predicts the existence of antimatter. And also, uniquely describes its behavior. So the Dirac equation describes electrons, but also describes how anti-electrons are coupled to electrons. It's a much more complicated problem. How does a quantum mechanical wave behave at super high energies and super high velocities near C? Well, now we know because we have relativistic quantum mechanics. So you can think of a field theory as a theory that describes particles in space and time as probabilistic density fields that behave according to the laws of physics written out as equations of the field. Okay, nobody says equations of the field, but they should. Our recipe for QCD is as follows. You take quantum mechanics, you add relativity, and please remember, all of this is math. I'm saying words, but math, okay? Next thing you have to do is add photons. And it's kind of interesting that people even talk about photons before they talk about relativity, because photons are inherently relativistic particles. They can only be understood with relativity because they move at c. They are never not relativistic. Do you know what I mean? However, photons are also quantum mechanical particles because they have that wave particle behavior. So a complete description of photons requires relativity and also quantum mechanics. What we're talking about now is called QED, quantum electrodynamics. So classical electrodynamics is a very successful theory. It describes the behavior of charges and field lines in the macroscopic world. But to understand what's actually happening, you have to shrink down to the quantum mechanical level, and those two things actually have to agree as you cross that boundary. we know that, oh, the Coulomb force makes these magnets repel. What's happening at the quantum mechanical level? It looks like this. So imagine you have two electrons, okay? You shove them together. They feel the Coulomb force, but what's actually happening is that as these guys get close together, this one will emit a photon and recoil away, causing the force to go this way. This one will absorb that photon and recoil this way. So they push apart because they exchanged a photon. And that is what happens when you shove two magnets together. A whole bunch of electrons are emitting and absorbing a whole bunch of photons to cause them to push apart. The closer you get them together, the more that happens, the more electrons start interacting. This is a Feynman diagram. So you've probably seen them before. So on the x-axis is space, on the y-axis is time. You see two electrons kind of moving together in space. One emits a photon, gets kicked away. One absorbs a photon, gets kicked away. That is what happens when you try to shove two magnets together. But that's also what happens if you try to shove two anythings together. Have you ever wondered why you can't smush your hands through each other? It's because of the electromagnetic force. It's because of electrons. The electromagnetic force is the reason mass takes up space. The electromagnetic force is the reason why you can't punch your hand through a wall. It's all QED. QED is a beautiful, beautiful theory. It uniquely and completely describes how photons interact with matter. Every single thing you know and touch and love can be described with QED. Why is the sky blue? Why do I have a reflection? Why do atoms have unique spectra? Why do hydrocarbons take the shape they do? How did evolution happen at a physical level? QED. It's all electrons, babe. I almost question why you would want to go further. Like, QED is the most interesting thing, and yet, people want to talk about what's going on in a proton? Who cares what's going on in a proton? You could just stop here. You ever wonder how holograms work? Don't you want me to tell you how holograms work? No? You clicked on a video called QCD. That's on you. I'm gonna stall talking about the inside of protons because... And inside the proton are the three quarks and all the gluons, which are massless particles that are just energy, keeping all this together. Okay. So a proton, which makes up everything, even the neutrons, all the mass, is three quarks and some gluons. And this is what it makes me, I don't know, does anyone else experience just like this anxiety when you think about this? The energy of a proton has this value. The energy of a single quark has this value. 1% of the proton is mass. Mass as we think of it. 1%. The rest is energy. I don't like it. It's hard. It just kind of creeps me out a little bit. Like everything you know and touch and love is just energy balled up together. And like I know from the energy mass equivalence that has to be the case. And like maybe I'm just a pathetic philosopher and I can't handle thinking about big things. But the idea that all the protons are just 1% mass, it's weird for me. I'm gonna stall talking about the inside of protons because for reasons. Let's talk about Feynman diagrams for a second. There's something interesting about Feynman diagrams. I should mention that these Feynman diagrams are like cartoons and not the actual physics. When you see a Feynman diagram, what you're looking at is a trick on the order with which to write down 75 path integrals, and then you evaluate those path integrals. Like the Feynman diagrams are a trick to make the math easier, but they are not the math. QED is backed up by actual math. I just want to make that clear. This is not quantum electrodynamics. This is a cartoon. I should describe his path integral formulation of QED. So the field theory version of that math is that you have this big wave function, field equation that is describing like space and time and where that particle is going to be based on this operator notation. And Richard Feynman did the same math. It's mathematically equivalent, but instead he described a path integral where you have point A and point B for your particle, and then you can just sum over all the possible paths, even paths that wouldn't exist and would be impossible for that particle to take, and you can find their relative probabilities and solve the problem and get the exact same answer. So it's two ways to solve the same problem. And Richard Feynman also had these little cartoons, which made it super easy to do it this way. So people started really liking this as like a better way to do it. But these are mathematically equivalent. Okay. The issue is when you move to QCD. It gets a lot more complicated because of all the things I mentioned up top. Like you have more quarks, you have more gluons. The gluons have color charge, which means they interact with your quarks and also with each other. So the field theory formalism is very complicated, but the path integral formalism gets so much more complicated. The diagrams, the Feynman diagrams in QCD, they're numerous. They interact with each other differently. They have a lot more points on them. They're much harder to do those path integrals. So if you learn QED with Feynman diagrams and path integrals and you move to QCD, you're like, oh shit, this is way harder. I can't do this. But if you learned QED, the field theory way, and you move on to QCD, it's like a little bit harder. I mean, it's demonstrably harder, but like you know how to do it because you've done like the little baby easy QED problems, you know. So there's this discussion on should we even teach these Feynman diagrams, which trick the students into thinking they understand something when they don't, and then they move on to the next subject and they're just confused and they have all these bad habits. Or should we just teach them the standard way so that they understand it when they get to the next topic? And then also it's like, okay, but how many students are actually going to take QCD? Do we really have to worry about this? And it's just a really interesting discussion in like physics education at the highest level. Like, how should you teach this topic? And I think it's really fascinating. This might be something people, I don't know what people are interested in. I'm interested in it because I think education is very interesting, but it also shows you like how the field of physics changes so slowly over time, because QED, a relatively new but very successful theory from the late 60s, is still being like, how do we teach this? Years, decades later. How do we teach this? What's the best way? I just think that's really interesting. However, my beef with the Feynman diagrams is, of course, that sometimes people look at them and they think that antimatter goes back in time. Like there's a little arrow convention to let you know that it's a little antimatter guy, but that doesn't mean it's actually going back in time. This is a cartoon. It's just a picture. That's not what it, you can't go back in time. Antimatter doesn't go back in time. That's why I don't like these diagrams. I think it's just like a personal beef. I think it's bad for like public consumption of physics information, but they are really nice to look at, and they're really good at explaining things like beta decay, you know, which I'm going to use the Feynman diagram to explain beta decay to you in 1 second. So ongoing discussion. Should we throw out the Feynman diagrams? I don't know. I do want to make sure that you don't leave this video thinking like Feynman was a dumbass. His stupid diagrams. No, the real interesting thing is that he developed this way of doing field theory with path integrals. And the path integral way to solve these problems becomes really, really, really important when you start having computers do QCD for you, because it's impossible for you to do those problems on your own. So, hot take, Richard Feynman deserved his Nobel Prize, actually. Okay, so our little recipe for QCD, I got distracted, I'm sorry. You take quantum mechanics, you add in a little relativity, you throw in the photons, you get QED, a very beautiful theory that describes how matter interacts with light. But you want to go in, you want to go more inside, so like let's crack open this nucleus, you know? I know what you're saying. QED sounds great, but it doesn't explain beta decay, does it? Beta decay is where inside a nucleus, a proton or a neutron emits an electron or an anti-electron and becomes a neutron or a proton. That's what beta decay is. I know what you're saying. QED doesn't describe beta decay, and it seems like electrons are involved, right? So here's the Feynman diagram for beta decay. So remember, space is on the x-axis, time is going up, and you have a neutron decays into a proton. So this neutron is just hanging out. All of a sudden, it emits a W boson. We don't care about that. And the quark that emitted that boson changes flavor and becomes a different type of quark, which means your neutron turns into a proton. That's what beta decay is. It can also happen the other way, where a proton emits a boson and changes the flavor of that quark and it becomes a neutron. So this is very similar to the previous Feynman diagram we looked at, where the electrons were interacting with each other. But here, the force mediator is not a photon, it's this W boson. And these bosons are very interesting because they're massive. This is a weak force interaction. So in the weak force, the force mediator is a W or a Z boson, and these guys are super massive, you know, compared to a proton and a neutron. They're more massive than those guys. And that's actually the reason why the weak force is so weak. Those guys are massive. They can't go very far, so the range of this interaction is short. That's pretty cool. This also explains why free neutrons don't live that long. If you hold a neutron in your hand and it's not inside a nucleus, it's just energetically favorable that it will emit a W boson and turn into a proton. The lifetime of a neutron is 15 minutes. However, a proton is really stable, like lifetime of the universe stable. You hold a proton in your hand and it will just chill, because the beta plus reaction is not energetically favorable unless the daughter products of that reaction will be lower energy. I want to remind you that this little Feynman diagram is a very pretty picture, but represents a very complicated type of math. It's either like a field theory with field equations or an infinite number of path integrals to describe the probability of this interaction happening. It's probabilistic, we measure it with experiments, and there's a ton of math there, okay? Even if you looked at this and you were like, I'm gonna do this math with a computer, because you can't do it, and you said, when will the neutron in my hand decay? You can't get an answer. You can say within 15 minutes, probably, but you don't get like an exact time, because even in this, quantum mechanics is a probabilistic endeavor, right? You get a probability of an event happening in a certain time. You can never nail it down and figure out when exactly it will happen. In order to test the results of this math, to test the actual probabilistic result we get, we do a ton of experiments to make sure that what is happening in reality matches the expectation of this math. I know that I haven't done any math and I'm not going to do any math, but I really want you to understand that underlying these little diagrams, underlying these experiments, underlying, you know, me just saying, oh, the halftime of this little neutron is about 15 minutes. All of it is math. And to quote the people who write high energy physics textbook, that procedure is very technical and out of the scope of this work. Beta decay is a description of the weak force, which is also a successful field theory. It's called quantum flavor dynamics. Not usually, because that sounds so stupid, but it's called the flavor because the quarks in the proton or the neutrons change flavor when the proton or the neutron decays into something else. Usually, though, people just describe the electroweak force, like the combination of QED with this guy, and no one really says quantum flavor dynamics. I actually hate that. Like, I don't like the sound of it. What it does tell you is that just like we can describe the interaction of photons with matter by studying quantum electrodynamics, a field theory of electrons, we can make a successful field theory of the quarks inside protons. So now we are finally ready to move on to quantum chromodynamics, a field theory for quarks. So we started with quantum mechanics. We added relativity, we added photons, we got a QED, a successful description of light interacting with matter, all through electrons. It's all about electrons, babe. And now we have moved into the nucleus, and we're gonna like just peek inside that proton and do some QCD. I mean, we're not. I'm just gonna explain why it's really hard. So do you remember the joke where I said people will take a class called QCD and be all excited to learn QCD, and the first thing the professor will say is like, let's start with QED. Let's go back to QED for a second. So the way math in QED works is that all of the problems are too complicated to solve. I did this video on the hydrogen atom, and I made this big announcement that I was doing the one problem that you could solve in quantum mechanics analytically, and that remains true. You can't actually do QED. I mean, you can do the tricks, but it's all tricks. So the QED approach to solving problems is deciding what problem you want to solve and then simplify it to the absolute simplest version of that problem and then perturb it a little. Make it a little bit harder so you can still do it, but your answer is more realistic. And you perturb it and you perturb it until the answers you start getting kind of converge. So you start with something simple and you just kind of add little elements to your mathematical model until it matches-ish, as good as you need it to be to get the answer. You perturb the model until you get something that looks like what you're trying to solve. And you make sure you don't go too far, because then the problem becomes unsolvable. And then you solve that problem. You solve a little easy version of the problem. In QED, in quantum electrodynamics, this works really nicely because it's really easy to see which path integrals are most important, which Feynman diagrams are most likely to happen, which part of the wave equation is it most likely that you'll find the electron. In QED, it's pretty easy to find that important thing. It's nice and intuitive to tell which interactions are most likely. And also, in QED, you just have way less parameters. Remember, QED, you have one photon and it doesn't have electric charge. In QCD, you have 8 types of gluons and they all have color charge. They all interact with each other. They all interact with the quarks. It's insanely more complicated. It's not tractable. Is that the math word? Impossible to do analytically. You cannot do QCD analytically. The fun little Dirac equation where I was like, look, now you're tracking 4 things. You have spin up, spin down electrons, and then spin up and spin down anti-electrons. Isn't that fun? It's not fun anymore. There's 8 gluons. There's 8 types of gluons. Oh no! And also everything's balled up. It's so close together. It's such a short time scale that the quantum mechanical effects are huge. It's so many things can happen and do happen. And also you can't just start crossing things out like in QED. QED is kid stuff. It's easy. QCD not so much. The gluons interact with each other. Imagine if the photons... No. This is tricky business. QCD is hard. I talked about QED as every single person does because QED, it's kind of, you can follow the math. You can see the math get bigger. You can see all the probabilities start adding up. Sometimes in QED, you have 40 Feynman diagrams and you have to add up the probabilities of each one to get a nice little answer. In QCD, uncountable Feynman diagrams. Impossible to figure out even how to set up the problem. This seems hard. This is impossible. But, Feynman's path integrals actually saved the day because you don't have to do it analytically. You can do it numerically. You can write, it's called a QCD on the lattice. So you take space and time and you put it on a grid and you take your little path integral. Remember, you have point A for some quark and point B, and there's an infinite number of ways it could go and how it's going to interact with all the gluons, and you got all the fields and stuff, and you just shove all of that into a computer on a nice little grid where time is moving, and you can figure out which is the important interaction, and you can randomly seed your grid with paths, and you can see what's the important thing and what you can throw away, and you can do this enough times where you get a pretty good idea of what the answer is. You didn't solve it analytically. You did a little baby version. You perturbed the model. It was huge and it was impossible, but you added enough to get an idea of what the answer could be. QCD, unlike QED, which is a mathematically rigorous proven thing, QCD has been verified experimentally all the time. The computer simulations give really nice results that reflect the world, but mathematically, we just can't do it, which is why it's so hard to explain. If you and I are standing in front of a blackboard and I'm like, what's your math background? I could probably show you QED. I could derive the Dirac equation for you and we could talk about it. I could not do QCD on a blackboard. I would first have to take you through QED and then we would have to pull out a computer and write up a simulation. Do you know what I mean? You can't explain it to a 6-year-old because it takes 4 years of undergrad and 4 years of grad school to get to the point where someone's like, and now you too can write a computer program and try to do a QCD problem. So QCD is a purely numerical theory, but it's incredibly powerful at predicting experimental results. And of course, when I say experimental results, is like you model the QCD interaction you want to model, and it spits out a bunch of probabilities of what's going to happen, and you run a bunch of experiments and you get those same answers. It gives you probabilities. It doesn't tell you what's going to happen each individual time. It tells you the phase space of what's going to happen, and that's what the experiments verify. So that's it. That's what QCD is. QCD is a bunch of non-solvable math that we use computer programs to like simulate, and it's incredibly successful at predicting experiments. QCD describes what's going on in the proton by modeling all the options and showing you which ones are the most probable. What goes on in a proton is incredibly complicated, but not nearly as interesting as what the electrons do. So, how did this go? Do you feel like you know what QCD is now, even though like I didn't say the word gauge invariance or abelian or Clifford? Oh my god, what are some more? Asymptotic freedom, renormalization. I didn't say any of the words. We didn't do any of the math. But, you know, second quantization, we did it. What do you think? QCD. Are you into it? Are we into it now? That was QCD. Thanks for watching. Like and subscribe.